Okay, so let's do the last of these physics-like lectures, and so let's go over the vibrating rigid beam. And so this is basically when we have, instead of a guitar where we have a flexible string, we have a rigid beam. So think a xylophone, right? A long rigid beam. Now we're gonna all the setup is going to be very similar, and we're going to skip really all the physics. Just want to show you that basically you get by different if you get a different equation, that you get a different instrument. So by figuring out what sort of equation your type of instrument satisfy, you can figure out how it should sound, right? So we'll figure out how at least a very simple model of a xylophone sounds. Okay, so we have this rigid beam, and it bends up and down, and it's going to be fixed at the end points again, right? And y is going to be displacement, so it's going to go up and down again. It's sort of very similar. Except now it's a rigid beam instead of a string, right? So I'm depicting it as a sort of a thicker thing, right, over here. Now, and again, we're going to have it's going to be of length L, right? Now, if we write down the equation, and again we're going to skip the physics of what it is. It's sort of similar to the wave equation. Except there is this constant, instead of being c squared, it's a to the fourth, and it's also, there's really an extra minus sign. So instead of this equaling this, it's plus over here. But there's one other difference, and that's maybe the key difference here, is that this is a fourth order, right? This is 4 derivatives in x, and only 2 derivatives in t over here. Right, so this is basically the type of equation that a xylophone would satisfy, or some sort of a percussion instrument where you have sort of a long thin beam that is hinged at the endpoints, where it's fixed at certain points, but it's allowed to sort of move up and down. It really looks sort of like this. It's not, if you really fix it at the ends, you'd get something different. If it was a free end, again, you'd get something different. So this is not. This is sort of we're looking at a very special situation, but this is what you would get at a very simple xylophone. It's sort of the beam sort of rests at the ends, and it's sort of acting like a hinge, right? Xylophone is more complicated, but again, a very simple example of it. So we have these boundary conditions that when x is 0, right, the beam is staying put, and the same thing when x is L. And very similar to the wave equation for the guitar string. But now, because of these 4 derivatives, it turns out that basically, for these kind of equations, you sort of need as many side conditions as you have orders. Let's not worry about why, but it's true. So in the x direction, I actually don't need 2, I need 4 conditions. And it turns out that the right conditions are that the second derivative is 0, and that's really just saying that there's nothing trying to bend it further, right? Because if you remember from calculus, the second derivative really tells you how is a graph bent, right? And so this is basically saying it's not bending it. Nothing is bending the beam at the ends, right? So let's just again, we're skipping the physics, right? So I didn't even tell you what this a to the fourth was. I mean, clearly you can figure it out from the material and various other things. You can figure out what this constant is. But again, let's not worry about it. It's just some number. Everything is just some number. Okay. So now we have we could still try something like sine of pi over L times x, right? Just like before, right? So if we if we plug that in, that satisfies both of these all of these sine conditions. So that works nicely. But now what we'll need is we need to really balance it out, because this equation needs to be satisfied. There's going to have to be this plus sign, minus sign. That actually comes up before, because of this 4 derivatives versus 2 derivatives. But there's another bit in the balancing it, because I'm taking 4 derivatives over here in the x direction. There's 4 4 factors of pi over L will come out, right? Whereas over here, when I take the 2 derivatives, it's only 2 factors of whatever's inside will come out. So to balance it, we'll multiply by this guy, and this a, this is going to be to balance out this a, right? Well, you'll see exactly how it works, once we check it. But let's try this solution. Okay. So let's just compute the various derivatives, right? I'm going to compute one part of it. So a to the fourth times the fourth derivative of y, and well, fourth derivative of sine is just sine, right? Actually, we saw that the second derivative was minus, but once you take 4 derivatives, the minus again disappears, and I have to apply chain rule 4 times, so I get this pi over L to the fourth, right? So this is the constant that I get in front, right? And otherwise I just get sine and sine again, right? So that's just a little bit of calculus. And over here, this is very similar to what we did before, but now I get sine, and there's a typo. I just noticed a typo. There should be a minus sign over here, right? Because there's if I differentiate the sign twice, I get a minus sign. All right, so there's a typo in the notes. I'll fix it before I'll post them. So that means that we'll get if we add up these guys, that we'll get 0, right? Because they subtract because of this minus sign, right? And this constant out in front is the same as out here, right? That's because out here I applied the chain rule only twice, but I looked at the square of what I need, right? So I get it. I get the fourth power, right? All right. So I have a solution, and in the same way as before, I can stick in integers n, right? Into this solution, I get solutions that look like this, right? That have an n in there, coming out. So I get different frequencies, right? Again, I get some overtones when this beam vibrates. And if we make this, again, making this simplifying assumption, just we don't have to worry about those cosines, right? So in the t variable, otherwise there would be a cosine. Let's not worry about it. So we get our complete solution. It's how how the beam sounds. It looks like this, right? So I have this series is just a sum of different of different terms, right? There's the first term, that's when n equals 1. This is when n equals 2, and so on, right? Then I have what's n equals 3, n equals 4, and so on, right? Maybe for simplicity, what if we said just a equals to 1 and l equals to pi, and lots of these things cancel out, and we're going to write down what does this series look like. Okay, so we have, if for n equals 1, I just get sine x sine t. For n equals 2, the way this works is sine 2x sine 2 squared t is sine of 4t, right? Over here, I get sine 3x sine 9t. And over here, I get sine 3x sine 16t, right? What does that mean? That means that the sounds that I get, the overtones are, well, it's the fundamental, it's 4 times the fundamental, it's 9 times the fundamental, it's 16 times the fundamental. I'm missing a lot of overtones, right? If you think about how if we look at actually I'll talk about this composition activity afterwards, but if we look at how does a guitar sound, right? And let's say the first 10 overtones, right? So well, actually maybe the fundamental and first 9 overtones. Then what I get is let's say you get the string vibrates at 100 hertz. Then the fundamental and the overtones, I'm getting all these frequencies, right? But now for ignore this here. For a xylophone, I'm only getting the 100. I'm getting 4 times the 100, 4 times the fundamental, 9 times the fundamental, and then 16 times the fundamental. And so that's out of my range that I'm saying that I'm using here, right? I'm missing the 200, the 300, the 500, the 600, the 700, the 800, the 1000. And then I'd be missing a bunch more. And then I get the 1600 and so on, right? Now, what this means is that a xylophone will sound like, it won't sound exactly like a sine wave, but it will be a very sort of pure sound. It has very few overtones. And so it has a very different, what's called a timbre it's I guess the first musicians were lumberjacks, right? So how does anyway? So it has different set of overtones. So it gives a unique sound. Each instrument has a unique sound depending on what overtones are present, how much do they change in volumes as time goes on and stuff like that. And that's really that's what's called the timbre of the instrument. And so for a guitar, you're getting all the overtones. For a xylophone, you're only getting the square multiples, right? A sine wave, if you actually get some sort of a music instrument that just generated a sine wave, well, that wouldn't have any overtones. It would actually sound not that far away from a xylophone. And actually, a lot of xylophones are made so that because they are more complicated than this, and they are actually tuned so that the contribution of the other overtones is as little as possible, so that you're getting as pure a tone as possible. That's usually what a xylophone is trying to get. It's not going to be exactly a sine wave, but it's going to be much closer to a sine wave than a guitar string, right? Now, different instruments for various different reasons have, well, different timbres. So, for example, a clarinet only has the odd multiples, only the odd multiples of the fundamental, right? So a clarinet, so for example, thinking about again the 100 hertz, would have these, would have the 100, the 300, 500, 700, 900, right, and so on. 1100, 1300, and so on. So it would, that again would be a different type of sound. It's a slightly purer sound than a guitar, but it's still less pure of a sound than a xylophone, and it's clearly different from a xylophone, right? I mean, if you compare these two, I mean, this is a 400. This doesn't have a 400 in it. It has 300, 500, 700 that aren't in the xylophone, right? I guess it's sort of a very simplified xylophone, right? Not quite, if you find an actual xylophone in there, it will be different. Okay, so that's really, it is, maybe I just mention it. This is, when I do this in differential equations, and we do this in more detail, and this is basically this is the proof why if you listen to something like punk rock, why punk rockers do not use xylophones, right? Because you want sort of a very a much sort of harsher sound, much there should be sort of more it should be sort of more noisy, more, it shouldn't be pure, whereas from a xylophone you're getting sort of a very pure sound, right? So you're not gonna, if you're gonna do any type of rock music or a lot of modern music, probably xylophones are not the best instrument. So anyway, so what we're gonna do for homework this week is gonna be slightly different. So we're gonna try to get you to do this composition. So I guess now it's, everybody's on their own. So you want to come up with a composition, and using the website, and you want to write the same, do a melody, right? So no chords, just one note per line, but with overtones, and you want to write it in a guitar type timbre, then the same melody in a clarinet type timbre, and then in a xylophone like timbre. And so you want to use, so it's going to be in the notes. You want to use, and let's say up to the first 10 overtones. So you want to use these sort of frequencies. This is for 100 hertz. So of course for different different notes, you would use different, just use the same multiples, right? 1, 2, 3, 4, and so on, and here 1, 3, 5, 7, 9, and here 1, 4, 9, right? And you also, because you don't want all the overtones playing at the same volume. That wouldn't work out nice. So you want to also sort of figure out the right sort of instrument. And so what the software, what the website allows is, instead of writing out just the frequencies, if you then put a at symbol right after the frequency, and put a number between 0 and 1, so maybe 0.5. So if I do 440 at 0.5, it plays 440 at half the volume, right? So So, I could have a guitar. It still has a 100, 200, 300, 400, 500, 600, 700, 800, 900, 1000. But now I'm playing, now I figure out that maybe I want the 100 played at full volume, but the overtones, and this is generally the way it will be, the higher overtones are going to have lower volume. So maybe the 200 is going to be at half the volume, 300 and at sort of a third of a volume, maybe 400 and at a fifth of the volume, 500 at a fifth of the volume, 600 at a tenth of the volume, and so on, right? So that might make your instrument sound better, so you can sort of play around with that. So that's going to be the homework for this week. I'll set it up on WebWorks, so it's going to basically give you a text box, and then you paste your composition after you're happy with it in there and submit, right? Okay, so I'll post the notes. I'll fix that typo, and I'll set up the homework, and next week I guess Jay wants to talk about some composition techniques. So we're gonna move, again, change tactics. All right.